The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
John Kevern. I'm Associate Professor of Civil Engineering at University of Missouri, Kansas City. So the first one here is the effective optimization of silica fume on pervious concrete, and acknowledge our kind of study co-authors, Tony Kajendik. This really came out of there's pervious, been used everywhere. There's been kind of parts of the country that have started to use silica fume in their pervious, although there hadn't really been any substantial testing as to the benefits. And so they came to us and said, well, can we put together a study that looks at the effective dosage rate. So what I'm showing here is this is we've done a whole bunch of precast pervious concrete pavement sections or sidewalk sections for the city of Milwaukee. And so this is a hollow core 6-inch pervious concrete precast section that has silica fume in it, and this is our very technical of loading field loading test. So as long as you got really good subgrade, it has pretty good performance. So okay, so anecdotal evidence. Our motivation for the study. Anecdotal evidence has shown that that silica fume is beneficial in pervious concrete, both from it improved workability and it improved durability. And so the kind of durability, freeze-thaw in the field is a hard one to evaluate for pervious, because generally if we're going to have freeze-thaw distresses, it probably wasn't built correctly to begin with, and so it's hard to say the chicken or the egg. Is it freeze-thaw or is it poor construction? So durability in the field, specifically for pervious, was related to what they saw for surface abrasion. So they thought the surface was a tougher material. And they took out cores and did the 1747, the LA abrasion test, and said it was better than the alternative. So that's really what we're looking at for this study is does it impact workability, and does it impact durability? So this was really broken into kind of 3 phases. So you say if you want to optimize cementitious paste, especially one that we know can get quite sticky at higher dosages, and pervious, if anybody's placed pervious, we know that when it gets sticky, you start getting in trouble because you can't get sufficient compaction. It tends to dry out. The workers can't get it placed quick enough, and you're in trouble. So we say, all right, what's happening here? So the first one is some rheological testing on just the paste. Second phase was, if we are going to place these, what are the properties and durability, assuming we have independent void samples? So we're going to control the compaction method like we do in the field, and we're going to let the void content float depending on what the effects are to workability. And then the third phase is to compare those effects. Let's control for the voids and see what the response was. So this is a shot of a pervious concrete that has some silica fume in it that was saw cut. And so saw cutting pervious is if you've got a really good dense surface, you get a nice straight saw cut. If you've got kind of a marginal surface that's maybe prone to raveling, you'll tend to get it'll yank out a lot of particles. So this is just one showing that we indeed, for this sample, had really good, it was a really hard paste. It was allowed to be saw cut. Okay, so rheology. Rheology is the study of the behavior of fluids, and specifically for this, we're thinking about the paste that's surrounding our pervious particle. And so pervious concrete fundamentally we've got a chunk of aggregate, and then we have some film paste or some of just amount of paste that it takes just to satisfy the surface area of that aggregate. And then you're going to have a little bit of extra paste that adds your capillary paste that helps stick those things together. And so the idea is to, if you have too much capillary paste, then you've got regular concrete. You don't have enough capillary paste, you don't have sufficient bonding between those particles to resist any forces, and you just have cement-coated aggregate that's out in the field. We definitely don't want that. The kicker is if our paste is too mobile, then we can't get this to sufficiently surround that aggregate or kind of fill in those voids, create a meniscus. If it's too fluid, then it drains to the bottom, and that's not good. It could plug our paste or plug our base up, but in essence, we have no strength at the top, and we're in trouble. So, looking at this, so we say, all right, how can we characterize what this behavior is? And it's we use the concentric cylinder rheometer. So standard rheometer for ketchup. So this is why use it to get your Heinz ketchup to stick in the bottle for just the right amount of time. So fundamentally, if you took a pencil and you stuck a pencil in water and you went like this, doesn't have a whole lot of resistance. But I take my pencil and I stick it in molasses and I do it. You can feel how much more energy it takes to get that thing to spin. So that's fundamentally how a concentric cylinder rheometer works. So out of this, we get really two properties. We'll get the yield stress and the viscosity. So yield stress, how much energy it takes to get that fluid moving, and the viscosity is what's that resistance to keep it moving. And so the yield stress for Pervious is going to control how much paste you can get around that aggregate piece. So a real high yield stress means I can hold a real thick amount of paste around that. Viscosity, so the viscosity, that's going to control that workability. So that's going to control that capillary paste, or as I'm pushing it, how easy it is to move it across the ground. So they're semi-related. So you're probably not going to have a really low yield stress and a very high viscosity, but there are things like viscosity modifiers we can add that tweak one more than the other. Okay, so as we spin this thing, we get some units. So we're looking at our viscosity here is the kind of bottom graph, and our yield stress here is the top. And so this is just a standard Pervious concrete paste. So we're looking at 0.4 water to cement ratio, some air entrainment, some water reducers, some hydration stabilizer. And one thing we know with Pervious, it tends to stiffen over time, and because it's a low water to cement ratio, we tend to have short pot life on some of the admixtures. So here what we were looking at is just basic mixing performance. And so we mix it, we test it initially. The viscosity goes down as we get the water reducer nice and dispersed in the paste, and then it stiffens over time. And so we say once this was completely mixed, our paste, we had roughly 75 minutes of hold time on our paste if we kept mixing it, so we knew at least we didn't have a Pervious paste that had issues. So first thing we're going to do. Second one, we're going to look at what's the effect with dosage rate. So with these, we said we're going to mix for 10 minutes. So we saw that 10 minutes kind of got us down to a minimal level. And we look at as we go up with dosage rate, our yield stress increases until we get over about 5.5%, and then it drops down again, and that's at least for a little while. So we get above 5%, and we basically maximized our particle packing there, and then we've displaced for a while. We've got lots of really small particles, so it drops until we have too many in the system. Need to, I'd say, mention in this study we used undensified silica fume. We used densified. It's very hard to mix it in a paste, so this was used with undensified. The viscosity increased with dosage rate, but we noticed there at kind of 5.5%, it started to get very sticky. So looking at this, we're saying we'd anecdotally heard that around 5% was the sweet spot for Pervious, at least for a kind of regular dosage rates, not adjusting water reducer with dosage rate, but for a regular dosage rate, okay, I'll buy it. Somewhere around 5 and 5.5%. We do have some differences as to the rest of it. So we said 5% is good. Let's run with 5%. So second phase, we're going to use rounded river gravel. We're going to highlight changes to void content. We're going to have fixed compaction energy and kind of standard Pervious mix design. A little bit of sand in there, hydration stabilizer, water reducer, air entrainment. So these are averages of 3 samples. This is void content as measured by 1754, so the standard Pervious concrete void content. And so we saw that we did indeed have a decrease in voids at 5% silica fume dosage rate because we had a little bit more workability. Above that, 10% is a pretty high dose, 15, 20, 25. It got stickier, void content rose accordingly. We're going to look at, here's compressive and tensile strength over time for these samples. We had kind of maintained or similar compressive strength. So 7 days we're at 2,400. 28 days we're kind of 3,400 PSI. So these are all sulfur capped samples. Compressive strength, we didn't see any increase or decrease at that 5%, but we did see an increase in splitting tensile strength, which might suggest we have a little bit better bonding happening. And then above 10% and above, because the voids crept up, our strength also fell off. Freeze-Thaw durability, same samples, we'll run Freeze-Thaw durability. Designed, so this was designed to have kind of moderate performance, the control. So our control there, if we're using a mass loss basis, we say ran 2 to 250. 5%, because it was a little denser, had better performance. Anything above that dropped off, had similar yet relatively poor performance. So our void content did give us a little bit better freeze-thaw durability. So that was ASTM 666A, the wet, the terrible wet test that we don't like to use, yet we always use. So then the third phase was fix and voids. And so this is the interesting thing. If you look at most Pervious studies, is they'll make a bunch of cylinders, and then they go out and they have 5 different grad students kind of rod them in completely different fashions, and then you see correlations between things that don't have anything to do with the Pervious, and the data stinks, and you say, how can you draw any conclusions because you didn't have a correct design? So the thing what we like to do, or what you should do if you're trying to look at direct effects, is we're going to fix the voids, which means every single cylinder, every single beam, the fresh material is weighed out, and then we've got a hydraulic press, kind of looks like a can crusher, loaded in a tube. It presses it down. No humans touch the Pervious, so we pop out uniformly compacted cylinders that all weigh exactly what we want them to weigh, so our variability is low. So we looked at both limestone and river gravel on this part of the study. So we weighed them out. We did void testing. So our void testing on these, we wanted 20%. It was within the precision of the test. So statistically, they all had exactly the same void content. So effect with dosage rate, so this is limestone, and we looked at versions washed and unwashed. So this is just kind of regular limestone used in Kansas City. We did a little bit lower dosages because we know that 10, 15, 20 didn't do us any good. And so for our washed limestone, we did see an increase in strength up to our 5%, and then at 7 it dropped off. For our unwashed limestone, really 3 to 5% was similar. Kind of interesting thing, we've always always said for Pervious that you want to wash your river gravel, and limestone probably doesn't need to be washed as well because the limestone fines get incorporated into the paste. And, well, here we saw a substantial difference between washed and unwashed. For the river gravel, so this is kind of clean river gravel, washed and unwashed, not a whole lot of difference till we get to that 5% dosage, and then we actually had a bump or substantial strength increase in the unwashed river gravel. So the material that was on it and the silica fume helped to give us a little bit better bonding. Abrasion, so we did on the left is ASTM C944, so that's the grinding, rotary grinding on the surface, and we didn't see anything. So we had our unwashed limestone, we had a decrease in abrasion between 0 and 3%, and then everything else in the sample, or everything else in the study, there was no difference in that surface abrasion. And then this is our river gravel samples, and our river gravel samples we also didn't see any difference. So got a question mark there. These are all for in the grand scheme of 944 testing on Pervious. They're all really low values, and so out of that we can probably say that if we wanted to see a difference, maybe we should have mixed it for an hour or something like that, because we had really good performance all the way across the board. The 1747 is a little bit of a different story. So 1747, you make 4-inch by 4-inch cylinders that are 4 by 4 tall at the right density or right void content. You take 3 of those, you throw them in an LA abrasion machine with no balls. You run it 500 revolutions, and then you measure mass loss. And so it gives you a kind of relative idea for mixes, how durable they are. Our limestone had, so there's our limestone. We didn't see any difference in 1747 abrasion with or without our silica fume. For our river gravel, though, we in fact did. So we had a substantial decrease in mass loss when we had our silica fume in there. So looking at, if we looked at for our river gravel, if we looked at kind of paste aggregate for, kind of here's a shot of our control with the river gravel, and we had plenty of cups. So the aggregate pulled right out of the, in strength testing, we had plenty of aggregate paste bonding failure. And for the, if we had, here's our 5% sample, and we had, the majority of those were broken through the aggregate, so we could say that we probably had some ITZ improvements in our paste aggregate bonding. So Freeze-Thaw, we ran Freeze-Thaw on the fixed void samples, and turned out we had some limestone that wasn't particularly durable, and we had some river gravel that wasn't particularly durable. And so all I can say is, if you had bad aggregate, the silica fume didn't. There was no difference. It just had kind of poor performance all over the board. So there's no conclusions on that side of the Freeze-Thaw testing. So all right. So summary. Rheology says we got something happening around 5%. I'll buy that is that supports what we've seen in the field. At the higher void contents, 25% and above, we didn't see much difference. The concrete wasn't really strong enough to have good precision, and so we had quite a bit of similarity, but a big void, or big range in precision. At 20%, so a little bit stronger, we were able to see differences. When we didn't fix the void ratio, so what we do typically in the field, 5% had a little bit better workability, which resulted in better strength. When we fixed our void ratio, to look at it, 3 to 5% seemed to be the best. We did get an improvement in strength. We did get, for our gravel samples, improvement in abrasion resistance. For the limestone samples, couldn't really see any differences. So, all right.